Here's a problem we will use to understand the basics of the finite volume method, flow in a channel, and schematically that flow looks like this. So we have two parallel walls, one at the top and one at the bottom. We have uniform flow coming in, and at the exit we have the pressure. And typically where you have the flow leaving the flow domain, you specify the pressure. We would like to find the velocity and pressure distribution within the channel. We would also like to determine the wall friction. And once we know the wall friction, we can back out what is the power needed to pump the flow through this channel. And we'll make simplifications. And the simplifications are steady, 2D, laminar, incompressible. And these will simplify the underlying mathematical model that we need to solve. We looked at what these terms mean in the big ideas in fluid dynamics, and we'll make some of these assumptions as we go through the CFD case studies in ANSYS Fluent. So we'll come back to these terms. As we talked about in the pre-analysis, the first thing we need to do is to consider what is the mathematical model to be solved. So let's do that. The mathematical model consists of governing equations and boundary conditions. We will talk about the governing equations first, and then we'll talk about the boundary conditions. The first equation that we bring in is conservation of mass, or the continuity equation. In differential form, it looks like that, as we have talked about before in the big ideas in fluid dynamics. And that implies that the volume of a fluid particle moving within the flow cannot change. The next equation or set of equations we will bring in is the conservation of momentum, F equal to ma. And that looks like that, as we saw before. And that represents the net pressure force on an infinite small fluid particle. That represents the net viscous friction or viscous shear on the infinite small fluid particle, and these are written per unit volume. That's the acceleration and that's the density. So that's F and that's ma, everything written on a per volume basis. And the governing equations are defined in a domain that's shown over here. So you have the top wall, the bottom wall, this is the entrance to the channel, and that's the exit. We will use a Cartesian coordinate system, so x and y as indicated here, and decompose the velocity into components in the x and y directions. So we have two components of the velocity, and then we have pressure. The unknowns are the two components of velocity and pressure, and all of these are functions of x as well as y. So we have three unknown functions, and we have three equations, one from conservation of mass and two from conservation of momentum, one each in the x direction and y direction. That completes the governing equation, so let's talk about the boundary conditions. The boundary conditions are defined at the edges of the domain. At the left boundary, we have specified the velocity. So that's velocity in the x direction, some specified value. The velocity in the y direction is 0. At the outlet, we have the pressure, and that can be 1 atmosphere. The exact value doesn't matter. At the top boundary, we have both components of velocity is equal to 0. That's a no-slip condition. And similarly at the bottom boundary. So we have three velocity boundary conditions and one pressure boundary condition. That completes the definition of the mathematical model. And there is not an exact solution available to this problem except in a region downstream where the flow becomes fully developed. And we will, discuss what the fully developed flow is a little bit later. So if you haven't seen it before, you don't need to worry about it, and we will look at it as we go through the CFD case studies in ANSYS Fluent. it's humbling that even a relatively simple problem like this does not have an exact solution, or at least a straightforward exact solution. So how can we solve this numerically? Okay, that we can do. And we will do this using the finite volume method. So let's talk about that next.